Today for the main quick seminar, we are very pleased to have Professor Matthias Christandl from the University of Copenhagen, who is going to speak about fault-tolerant quantum input-output.
Okay. Thanks a lot. Thanks a lot for the invitation. It's a pleasure to be back here. I just checked, must have been in 2018. No, 2016, I think, that I've been here for a workshop on complexity theory on QMA, so faculty organized. Yeah, so it's a great pleasure to be back. Thanks for having me. I'm here today and tomorrow. So if you want to meet up or speak to me, just let me know, and I will find some time. I want to speak about a research topic I've been very excited about. I call it fault-tolerant quantum input-output. It's a line of research that actually started with my postdoc, ller-Hermes, and at the time, actually, Gottesman, who's also here, was a member of my group. And the question was that we wanted to study was really how do you communicate effectively, quantum communicate effectively when your encoder and decoder are actually noisy computers. And that sort of like started out a series of works and led to this paper, sort of like now it says 2024, but it took some time to get things in print. And now most lately, I've been working with Matthias Christandl, who's a postdoc in my group, and ller-Hermes from University of Fault. And we try to build now like basically subroutines of making this possible. So I want to tell you more about it. And yeah, so I'm working at University of Copenhagen. I'm actually in the Department of Mathematics, and Denmark is characterized by having larger foundations that actually own companies and that fund research. And one of them is Velux Foundations. They make the Velux company makes windows and slanted roofs, and with them, together with mathematical physicists, we established the Center QMath, and then so this is sort of like quantum information, mathematical physics, Bose-Einstein condensation, things in this direction. And the Novo Nordisk Foundation, which you may have heard of, their weight loss medication. They were interested in seeing what is the possible impact of quantum to the life sciences, and so we took this opportunity to make a research program on connecting QMath, in some sense, the research we're doing, topically to the outside world, so to chemistry and also to an experiment that's being built, like a neutral atom simulator. And actually, that's a picture you see of this neutral atom simulator at the Institute of Copenhagen. That's anyway, if you have any questions in the meantime, just interrupt me. How much time do I have?
So it's an hour for the talk plus Q&A.
All right.
Figure out the time.
But I want to first, yeah, probably very familiar with this, and but I first want to give you sort of like an introduction to fault-tolerant quantum computing in the way that I will kind of build on. You can see it as like maybe setting the scene for further discussion. Then I want to tell you about this fault-tolerant quantum input-output, and then I have two applications. One was this earlier one on fault-tolerant quantum communication, and in another one is more traditional. So we managed to use one of the tools for enhancing fault-tolerant computation with constant overhead. There's a lot of discussions about these constant overheads. So you want to kind of like make the constructions as efficient as possible. And we contributed some analysis that allows us to do it with more general noise models. But let's get going with just the setup. So of course we all want to factor numbers on quantum computer choice algorithms. So 15% 5 times 3. So I'm using this in different contexts. Maybe you have seen these examples. Does anyone know what the factors are?
11 times.
Yeah, it's 11 times 71, very good. Anyway, so there is also search, right? So you can search for this number. What do you guess? It's mine. You can take this one. It's Ernest Lyon, so my collaborator. Anyway, and this one I kind of thought, yeah, I had to make them longer, right? So, but the longest numbers, I think from Germany, I didn't know it's a big number. So in chemistry, you want to understand, this quantum Fault thing, you want to understand that molecules stop, right? So you want to understand, independent on the distance of your target molecule to say protein, you want to understand, what's the energy. Okay, so these are three kind of possible quantum algorithms you could consider. And of course, the problem is that the assumption of noisy quantum computers is unrealistic. So if you have noise here, then this is all put into question. That's kind of what I put there. This is Wilmer Samson gate. Sure, it's still pretty sure. Anyway, and so here actually maybe it doesn't bind. So as soon as there's noise, we don't know what to do. And yeah. So how can we combat the noise? And of course, people started asking this question in the 90s. And so you pick a university gate set, you write down your gates. And so anyway, it's some kind of introduction. Of course, I'm talking to experts now, so just think of them as being setting the scene. So the qubits, they're implemented, well, I think, like, this probably all qubits implemented either in lines or atoms, superconducting devices, or maybe phonic qubits. And the errors, they have gates. Depending on who you ask, we're probably there in the range of 10 to the minus 2 to the 10 to the minus 4. I would say there are two reasons, maybe two main reasons for why you have these error rates and why it's hard to combating them. One reason is actually maybe approximation and the implementation in itself is one, but another one is the coherence, interaction with the environment, leading to maybe say damping or dephasing. Another one is imprecise implementation. I mean, I guess imprecise implementation could be by design or by just like you have a lack in control. So say you want to do a gate and you have a small over rotation, or you have leakage in the system. So these are different ways. You can combat them with error correction. Of course, here's how you do it when you have a classical bit. So you do a repetition code, 0 goes to 0, 0, 0, you get one error, and then you can do majority of decoding to get back to 0 and 1. And of course, the Shor code allows you to do it the quantum way. So you just have to live with the fact that you have both bit flips and phase flip errors, and you discretize your error set in this way. And you're basically doing twice this decoding, once for the phase and once for the bit error. Here's actually the circuit. That's the error correction circuit for the Shor circuit. I think I stole it. I stole it from Wikipedia. Oh yeah, even acknowledge it's written down there. Right. And if an error happens, so if you encode and an error happens here, then this error correction circuit is able to correct this error. Just like here, if one error only happened was possible, and here you have two types of errors, so like 9 qubits, and if only one error happens, then you can still correct it. So that's great. Error correction works. But then comes sort of like the point, and that is why my talking about error correction with its fault tolerance. It's like if the error happens here, namely if, say, the Hadamard gate gets an error, then what may happen is that the error spreads, because after this error happens, there are some gates, and even if there's noiseless, the error spreads. And then after I have encoded here, actually I have 3 errors. And then actually you cannot recover. So the error correction fails. And this is sort of like interesting, because classically, this essentially doesn't happen. So essentially, your computation classically is noise-free, and all the errors happen in storage or during transmission. And so you bring them into the code, and then once it's in the code, the error happens, and then afterwards you decode. But in quantum, the current devices and also what people think you can do in the years to come will actually be significantly affected by this case. The other case is still there. Still in memory, you will have errors, and still in transmission, you have errors. Maybe there are more, but certainly also in this scenario will happen. So you have to be kind of smarter, and that goes under the name fault-tolerant constructions. And there's a technology being built, and I kind of call it the technology. It's really like a toolbox of things people have developed that's still kind of advanced to do this. So you pick this universal gate, you write it, and already when you start talking about universal gate set, something starts changing, because you need to include also you need to include the identity gate, because like when you wait, right? We just wait the time step, and error might also happen at that time step. So it's a good idea to kind of like have that as part of your gate set. Yes.
So I was thought about it. So you said in classic computation, the errors cannot happen during gates.
Well, they can, of course, but they typically don't. So if I understand correctly, that in the computers here on our desks, they just don't.
They're so fast.
Well, there are so few. Yeah, there's so few. There's apparently some applications where you do need it, but whenever I talk to someone who knows a little bit about it, they don't spread. So you can do away with repeating things a few times. That's kind of fine. But I haven't really met anyone who properly uses this error correction classically. From Neumann correctly, I did some behavior. Yeah, but it's sort of like interesting when I talk about a gate set. We also include a few more gates, like for instance, like the identity gate, but also like prepare zero. Okay, so like here's a gate, right? It's like a isomorphy, you can say. It's like it prepares zero, or prepares a one, or partial trace, throws something out. So it's that's what I would call this, what I would call the circuit. And so the gate will be replaced, and then the fault-tolerant construction. Every gate will be replaced by a gadget. So it's not only like the qubit will be replaced by like an encoded qubit, but you also need to talk about the circuit. So then, that happens. So every gate will be every qubit will be replaced, but also every gate has to be replaced by some kind of procedure, by some kind of gate. So here, for instance, this is a seven qubit replacement. So one goes to the 7, and then of course, what happens to your circuit? This circuit will be transformed into such a circuit. And I'd like to introduce this notation of like this triangle. Maybe this is sort of like for the experts, we mostly use codes. I personally we use mostly codes that correct 2 or more errors. But you can also do it with like 1 error codes, but that's not such a, here is for instance an example. They become massively big. There's an 11 qubit code. Yeah, it's 1 qubit code. So you encode 1 qubit into 11 qubits. And with that code, actually code corrects 2 errors. It will be useful to have somehow you need a little bit of stronger codes to do that. Okay. But there are of course also cases where you can get away with other codes. But as soon as you start talking about fault tolerance, there's a lot of things you have to kind of like adjust, and you have to make a setting in some sense. Yeah, so then what happens, you concatenate for better error suppression. So right, once you encode once your qubit into this code, then typically what happens when the physical qubits are affected by an error delta, then after you have encoded them, they're affected by an error delta squared. So, and of course that only gets you so far. So you want to suppress it to some much lower error, then you have to do this multiple times. This would be one way of doing it. And if you do that, actually the error rate, the number of qubits increases exponentially, right? When you do this layer by layer. But luckily now, the gates, the quality improves doubly exponentially. Okay, so that's nice. So then you can still do it. So you will only do like a very small number of layers, and like double logarithmic layers. All right, so I wrote it down here just for completeness. Okay, so you know there is this code. It has these states like the Shor code. You know, you can write down this logical state, and you can then discuss how to act on it. Okay, but that was just really for flashing. There is something that will be important for us. It's also decoding. Okay, so you know, it's like the opposite in some sense. Okay, so you have it in many ways encoded, and then you decode. Oh, there's not more information here. Oh, that's all I'm going to tell you about it. But I have these triangles. Now I introduced my notation for you. Okay, so how does fault-tolerant quantum computing then work? You start with your input, like you should think of you know, your big number that you want to factor. Then you start encoding this input with these procedures. Okay, but it's kind of like a fix, right? It's a classical thing, right? So in some sense, it prepares some specific code state for you. Then you run your encoded circuit. Now I told you before, you take your circuit and then you replace all the gadgets. You run that encoded circuit, then you decode, then you get the output. That's how it works. And the input here and the output, they're kind of stable. So they're like, I think you should think of them as being, you know, the classical bits being stable. You could also think of them being already kind of error corrected, but I think it's better if you think of them as being really a different object. These classical wires, they don't experience errors. Now in the constructions, when errors happen, right? When errors happen, the constructions need to be such that the errors don't spread. So this effect I showed you for this like Shor code, that shouldn't happen. Yeah, and so that requires some kind of special construction and special code so that they don't spread. And I think this is sort of like an interesting. So the error correction. So basically, every time you do this, every time you do a gate, you can think of that. So you do a gate, like an encoded gate, and after that gate, you run a procedure of error correction. Okay, so the entire circuit here is like is a lot of error correction. It's happening the whole time. Okay? It's like error correction happening after every single gate, you know. So the whole time there's error correction happening, and you can think of that this construction needs to be such that the error correction, it just pulls out more errors than it itself puts in, right? Because the error correction and it will, of course, is also a circuit. It will inject errors into the system, but you will have to suck out more errors than you inject. So in that sense, it's a little bit like a refrigerator you have standing at home. That you know, it's cooling your system. You know, but the machine itself will also like heat up what's in it, but it cools it more than it heats it up. Okay. So that's sort of like what I wanted to tell you about it. I have one slide. Usually now, of course, the question comes. I mentioned already a little bit about error models, and as I have a few more details there, I think for error models, it's very nice to think of errors happening probabilistically, and I think this is why a lot of the literature there also does that. And here's a common way of thinking about it. So, say after each gate, each wire is affected by either Pauli X, Y, or Z error with a probability delta. Okay, so you run some gate and like a single qubit gate, and afterwards that happens. This is one error model, Pauli noise model, and it's very nice because it's because the codes, all of these codes, they're kind of like analyzed with respect to X, Y, and Z errors. It's like if I say one error, then you know it's like, and they are, you know, they behave very nicely with respect to Pauli errors. And so this is like the simplest error model in some sense. And maybe if you like it to in a map, you can also think that the rho, the state, is kept with probability 1 minus delta, and probability delta over 3, one of the errors happens. This one other way of thinking about it. Yeah. So there's another way, a little more general, could be that like, okay, so with probability 1 minus delta, nothing happens, and probability delta, some other map happens. Okay, something else happens, and I don't control exactly what it is, but it may be not as easy as this. So that's another a more general one, and typically goes under the names just stochastic noise or locally stochastic noise. And and there are different ways of now discussing like how correlated the errors are that happen. But I think a nice way of thinking about it is that they happen independently on the locations of the circuit. Okay, so you have your circuit layout, and you just build the errors independently there. And note that even though you throw them independently there, it's not easy. And the reason is that if an error happens, so now I took it like after this Hadamard gave put an X error, and now right, this error, if it happens just here, but it afterwards is gate. And so the gate will actually make the error, on the qubit errors that you have, effectively when qubits are correlated then. Okay, so it's not somehow simple because of that. So, and I think this is sort of like, in my opinion, this is a very natural noise model that you can now, because many of the things are analyzed on the layers, like on what happens on the qubits, and there you need to analyze the slightly more general thing. You could now start to try to generalize the circuit noise model as well a little bit. But I prefer talking about this model of having like IID noise on the locations. Does that make sense? Yeah. So, and the analysis of this stochastic noise models have the advantage that you can do kind of like a pattern analysis. You can say like, okay, here is like a pattern of errors that happen. And then I can analyze the probability of a particular pattern happening, etc. And this allows you actually, in many situations, to go quite far. So first of all, it allows you to, it allows you to go quite far in the analysis. It also actually allows you to do simulations. Because you can just, so for instance, if you restrict your poly noise, a lot of the situations where people like analyze thresholds, you could then go and say like, okay, I'm just like propagating my errors, right? So I'm doing like an error propagation, I study that, and that's very convenient. And of course, in the work of Dan and Gottesman, in others, this probabilistic analysis is very possible. So there is another, maybe a more realistic one, because as I say, this noise model here, it doesn't capture amplitude damping noise. And amplitude damping noise is arguably one of the most important noise models, certainly in superconducting qubits, but in many others, you have spontaneous emissions, and they will lead to amplitude damping noise. It also doesn't cover the over rotation, right? So if you just have a small rotation, it will not cover it. And here, so in this more realistic noise models, you would say, okay, so here's one. Each gate is replaced by some channel that's delta close and diamond norm. I really like that. So you take your circuit here, and you just imagine that each gate, so this gate here, is just replaced by something else, by some map that's just delta close. Okay, and the same for the two qubit gates. And now here, well, it will be replaced by that. So you take all the locations, you replace them by something else that's diamond norm close. And if you do that, you can capture, of course, these more general noise models, but it includes those up here. But of course, you're now challenged a little bit of having to do an analysis of like diamond norm bounds on these maps, and you have a new formalism, and it took us some time to understand. I will also tell you why we chose it. We working in a framework that I think was first provoked by Alexei Kitaev, to study this fault-tolerant formalism. We found that a good formalism for us to work in. So then that's sort of like, okay, so as soon as you start talking about fault tolerance, you have to kind of like choose. You have to make choices. You choose a noise model, you choose a formalism to analyze it, etc. Yeah.
And then so the threshold theorem still works also for this parent norm?
Yeah, you can do threshold theorems there.
And in the stochastic noise model, do you have somehow have to, because you said you choose this lambda as something different than eventually, so but how do you like qualify it? Do you have to say it really has to be different for the entity, just from norm distance from entity, or how do you?
No, I think usually it's driven by what you can analyze, right? So there's somehow 3 levels of analysis, I think. So like basically maybe there are more, but 3 levels of analysis. One where you sort of like you need the property of having X, Y, Z errors like this being thrown, and then when you do these error path analyses, very often you actually don't need to know what it is. And then the noise model in reality is much more. You can do anything of this form, and the analysis will go through. Right? You basically want to have you want to have some construction, and then you want to say like, oh, construction works, like algorithm works, everything is, you have a threshold theorem for this and that situation. And then you notice like, oh, and analyze it, oh, it actually works, even though I have a more general noise model. And just want to emphasize that. I think there are these 2, and then there is this third one here. And analysis here, of course, probabilistic analysis will not work anymore directly. Of course, what very often will be the case that you sort of bootstrap from probabilistic analysis. You do some probabilistic analysis, and then you write your operators as linear combinations of these things, and then you have to put it back together to get your bounds. So it's not like, I'm not saying like very often in analysis here under the hood, you will have to generalize something from here, and it uses that in an integral way. I'm just saying, like, if you want to make a statement like this, you really need to have somehow a different mathematical formalism to even like talk about them. That is what matters. And it would be harder, like, say, to do simulations because suddenly, you have to talk about it. All right, yeah, but the first paper I looked at in this context was this Aliferis Gottesman Presfield paper from 2006. Actually, it also works with these. Here's the statement. Here's the threshold theorem. I think this is sort of like one way. There is a threshold delta such that for all delta small and delta 0, and all circuits and inputs, this is your perfect algorithm, and this is the simulation I just explained to you. But where I throw noise on, right, then the threshold theorem tells you that the output here is very close to the output here, in the sense of like the probability that the output for this one is identical to the output this one here. You want to bound that probability, or you want to bound the probability this is not the same as this one. And so here is like the probability of the output at k level encoding. So you k level this encoding at delta noise, the probability is not the output at 0 level at 0 noise is smaller than, and you see how it works. It works basically via a union bound over number of gates. And then by this encoding, so delta divided by delta 0. So if you imagine you have some threshold delta 0, you put yourself with your delta at like half of that, right? Then it says here half to 2 to the k, okay? So if your circuit has like a polynomial number of gates, it's actually sufficient, to take like log number of gates in the input. So you get some overhead, okay, with this kind of like argument and construction, and people have been working to improve these things, etc. But I thought it was good to give you somehow something concrete for understanding. Any questions for this? Yes.
How far do you get if you give up this locality, so you have correlated noise, for example?
I think, as I said before, I think in depending on the situation, I think because the analysis of the stochastic analysis and fairness model, you can relax some of the assumptions on the noise. So some also locally stochastic noise models. But for instance, in this Kitaev analysis, I think you really want to think of swapping every gate by something, right? You sort of like you don't really have a probability that you throw an error in one. So you just take a gate and you replace it by some other gate. In that sense, it's already correlated, right? So you could replace all the gates in some correlated fashion. But the correlation, you will have the correlation on the qubits. On the code, they will be correlated, but they will be correlated. Typically, the situation is analyzed as what people call locally stochastic noise. So this is noise that, well, I guess you could say has like exponential tails in the correlation. So I think as soon as you have like worse than exponential tails, like polynomial tails or something, then it gets harder. I don't actually know what the status is there, what people have on the walls. Yes.
On the previous slide, you had like the same delta for all the gates.
Yeah.
But you would also like some gates are much more higher fidelity.
Yeah.
Than like an
So I guess sure. So sure, I guess it's just has to be like below some delta zero. Yeah. So if the one I really like to think about is this one down here. Okay. So you're allowed to replace every gate by some gate that is delta close and diamond norm. Okay. So, if I would be in this framework, talk about noise models like this, it would be like the delta smaller than less than delta zero. Yeah. So then you could adjust. So no limit on like some gates being better or worse. But
So you can probably improve the bounds, so we take into account that.
sure, you can improve the balance. Yeah, sure. There's a whole industry on like trying to figure out what these thresholds are. Right, I'm not going to go to this discussion, but of course, now you can take that into an entire research field direction. Like, okay, in which situations should I use which codes? When is it affected, etc. So you can just think of me just taking the worst gate now here, and then that is what we're talking about. Yeah. So, yeah, but of course you can take that analysis to a more detailed level. Yeah. So I guess in this paper it's stochastic noise, not mistaken. But there are also statements for this Kitaev, for the general noise, etc. For the general noise model and so on. But I just wanted to make it kind of like concrete, so you've seen it more. But what's important for me is to emphasize is kind of like classical input, classical output. Okay, that's sort of the story. So I want to go to this, which is kind of like the title of my talk: quantum input output. Yeah, what if, right? So what if our noisy device interacts with a quantum black box? So you use a quantum computer and you have this noisy device you want to interact, right? What if you need to distribute the computation to computers based on different fault-tolerant architectures? So you got like some neutral atom simulator, you got some superqubits. I can't even remember what I put there. I think this is some picture of quantum dots. Okay, so you have like different, yeah.
So we're saying that the noisy device is supposed to act like a quantum computer, and the quantum black box is an ideal quantum computer.
Yeah, or just like you don't know. Okay, someone tells you like, okay, so you have my device. Here's my device. I built it. Okay, here's some other device. Let them interact in some quantum way, right? We do this the whole time, right? It's like if you just think of the set of like QMA or something, right? Some complexity class, it's like I have some verifier, there is someone else, and we're interacting, we're sending quantum information back and forth. Then I am in the situation that my quantum computer that I'm building is not outputting a classical string. It's outputting some kind of quantum thing. Right. That's sort of like what I mean, right? So I'm building something and I want it to interact with something else in a quantum way. Then, yeah, it's not standalone anymore. Maybe I'm getting some, like this quantum advice. Maybe someone gives me something and get some quantum advice. How am I going to deal with it? Or you need to distribute computation or you, if I shift the focus now on communication, or I need to communicate. So imagine I got my quantum computer, I built it here, my friend built another one, I have this communication line, I need to communicate. How do I do this? Okay. And all of these situations are not somehow, they're not directly at least covered by the situation from before, because there my quantum computer had a classical input, think big number, and classical output. Yeah, so more generally abstraction, what if we need to receive quantum information, right? Or send quantum information. So if we receive quantum information, we could now say, like, hey, please deliver it in my favorite quantum error correcting code. Right? So I'm providing the interface. Well, that puts the burden on the sender, right? Or you need to send quantum information. Well, just send it. We send it in our quantum favorite code. Well, that puts the burden on the receiver. So somehow, someone somehow needs to solve this problem of how do I put a quantum input there and quantum output. At least we need to start discussing it. Here is one concrete statement, and I want to mention here. It's in this recent paper with I guess maybe a year on the archive now with Omar Fawzi and Swami. So just for state preparation, just to be very some basic. Okay, so here is a circuit, and that circuit prepares a state. Okay, it's like classical input, all zero input, it prepares a state. And how would we do that, right? So now it's clear. It's clear that if errors happen in the circuit, I will not prepare the right state. So I have to kind of like do something. And here's what you can do. You could say like, okay, so let me take the zero, encode it into the all zero, then run the encoded circuit. Okay, but what I get at the output here is actually the desired output of my circuit, but as logical qubits. That's not what I want, right? So because that would be the situation that I give to the other person in my favorite code, in the architecture of my system. But if I just have to produce a specific state, well, I want to kind of like, want to prepare that. So I somehow, what I could try is I could try to just like decode it. Okay, so I just decode it, and then what the and somehow okay, hope for the best, right? Well, what will happen? What will happen? So let me see. Actually, so what will happen, of course, is that we want the situation to be robust against noise that happens. Right? And if the noise happens during the computation or even during the preparation, still things will be fine. But you see what you cannot avoid, and actually you cannot avoid it with any construction whatsoever, is that just at the very end, here in the decoding, or in any other construction, that at the very end, at the last qubit you touch, an error happens. Okay? It took me actually in the beginning, it took me some time to understand this point. So any circuit you may write down that tries to prepare this here will, the most clever construction, it will have a last gate. There will be a last layer of gates. And if this last layer of gates is affected by noise with probability of delta, then a delta fraction of the final qubits will be affected by noise. So you can't do better than that. And so the statement for the theorem is, and with low rate noise, I mean that, right? So like delta fraction, the statement of the theorem is that is achievable. Okay, so you can do that. So it's actually possible. So you require this, at least you will have that on, but actually this is achievable. And Yeah, as I said, it's optimal as the errors can happen at the end. And in the stochastic noise model, there is a previous work by Gottesman having also such statements. So there are different statements in literature about this, but I think for general noise model, this is one of the statements that we have in our paper. We have a similar statement for receiving information, okay, for like doing measurement. Yes.
So the point is sort of that, okay, you can make threshold theorem. So you say, I can make the script as long as I like, because I can have a sufficiently high correction rate.
Yes.
But then in the decoding, there could be an issue, right? So you say,
yes,
everything is fine until then, but then the last qubit might be the issue. So I have at least error delta if I want to decode.
Yeah, and of course it's not, yeah, so the last, I have at least an error delta at the end, but of course what might, it might be much worse, right?
Because so decoding.
Yeah, because I have decoding. So, and the way to think about it is that they come highly protected into the decoder. And so every time you shave off a level of protection, and because the protection is sort of like, is exponential, you sum basically, you have this exponential sum, and the sum over, of this exponential series still being a constant times your delta. And there's another complication actually, is that it looks like these errors would be uncorrelated here at the end, but it's not the case, because this circuit here, even though it's highly protected, there are gates here that will touch both of these qubits that have to be decoded. So there'll actually be correlations coming in, and you will see these correlations down here. So the noise, in contrast to what I said, you have at least this delta fraction, they will also be a little bit correlated. So you'll have to deal with that correlation. That is sort of like why I put it as this like box there of like, but they're locally stochastic. So in the noise model of locally stochastic, they're locally stochastic. I like to call it sometimes locally stochastic, but that's not if you're in the coherent noise one. But I think I personally call it somewhat adversarial. But okay, very good. Yeah, so I took this as an example of put it here. We have a similar statement for receiving quantum information. So now imagine you have basically a measurement, right? Now I should have had this, but we'll see it later. You have a measurement, then of course it's the other way around, right? So then you have this perfect measurement and the noise comes, you can push the noise to the other side of the measurement. So, and we also have statements for circuits that have both quantum input and output, but they're a bit difficult to handle, like in practical applications. So that's why I'm sort of like putting a little down with the bar. Okay. Okay, let me show you proof. Show you proof by pictures, and I have to speed up a little bit. Proof by pictures. Okay, so I want to show to you that this is actually the same as the other one. So what I'm doing, I'm inserting an ideal decoder-encoder pair. So basically, imagine I have quantum information in my code, I decode, and then so like my triangle now, this is like the one physical qubit. And here is kind of like the syndrome. Okay, so I have when I decode, I get a syndrome, and normally I'm using the syndrome to correct this down here. So I'm now passing the syndrome on, okay, to my encoder, and my encoder kind of like according to the syndrome puts the errors back on. Okay, this way I'm actually having the identity operation here, and so this way I have an identity. Now I can put this identity in here. Okay, so instead of like typical, and you will see in a minute why I'm doing this, but basically it's very hard to talk about. It's very hard to talk about noisy decoders. Okay, that's the basic reason. Okay, like no one can tell you what a noisy decoder is. Okay, so you want to kind of like replace your noisy decoder by a noiseless decoder, and then you do it this way. So you put this identity in here, then suddenly, it's great. So the noisy decoder moved into a noiseless decoder, and then so I'm doing that for all the qubits, and now I'm just looking at the part up to here. I'm like, if I have my circuit and errors happen, right, and then I have noiseless decoding, I know exactly what happens. Right, so up to here, I have noises. This noiseless decoding of my state in the code. I know what happens here, so I get some error syndrome, but otherwise I have my perfect circuit. And then these guys here together, they're kind of like noisy channels, right? So I have a perfect encoding channel, and then the noise decoding channel, and you can show that the noise of this here is kind of like rather weak. So actually, the first to discuss this was actually a paper by Michal Horoletsky and others. So so each of these channels here is close to the identity plus a bit of noise. But what, of course, for us is the tricky thing is that the error syndrome will correlate them. You'll see that now. So each of them is kind of like this error syndrome thing plus a little bit of noise. Now comes this perfect circuit, okay? Hopefully. And this error syndrome here, though, is like correlated. It's like feeding into this like channel, right? My noise channel here. And it's correlated. Oh yeah, because you see here, I have I had managed to replace my noisy decoder by a perfect decoder, and if I'm kind of like below the threshold, right, then my perfect decoding will actually decode this. This is sort of the property of variant codes.
Yeah, but what you say is good. Okay, but there can be still be errors in your main application of the like encoded circuit, right? So errors.
Yeah, there are errors, but like say here you but you have control over the errors. You have control over the errors until here. And
Small enough.
Yeah, small enough, but yeah, you know that by your normal analysis from the normal fault-tolerant theorem. Normally you would now say like I'm doing a measurement here, okay? But if you have a perfect decoder, it's also fine. I mean, like a perfect decoder is it's even better almost. And then and you know that the codes have the property that so there basically you get your perfect circuit here. And then you get your, but interestingly, you get this like the error syndrome here is still a bit correlated. So when you analyze each of the decoders and you figured out each of these boxes here, they were basically like a perfect encoder followed by a noisy decoder. Each of them is basically identity plus a little bit of noise. You can kind of analyze that. Then that's all great, but they get fed like a correlated error syndrome. So in this error syndrome, then it correlates things, but you can show that it has sort of like relatively low weight, okay? Because of that. Okay, that's roughly the idea of how to do this, how to prove these things. All right. Yeah. Okay. Good. Questions? More questions? Okay, so now let's apply this, okay? And so in some sense, so I'm telling you the story a bit backwards, because we kind of like started with this application and the way now, yeah, so like my presentation is not in chronological line of research, but showing you how to apply this now. So here's the problem, and it's like so the problem is, so let's say I want to apply it in quantum computation. So so this is our first communication setup a la Shen in the 1940s. I have an input, I have an encoder, it's just classical. I have a channel, noise channel, I have a decoder, I have an output. Just some notation, I have M input bits, I have N channel users, I have a capacity. The capacity is defined as the ratio of M divided by N, such that the probability that input not equals output small epsilon. I take N divided by N. I want to optimize over encoder and decoder. I look for best encoder and decoder, that's the supremo. I have fixed my N, I have fixed my epsilon. Then I make the block length larger, right? Limit N to infinity, but at fixed error rate. think of the error as being very small, 10 to minus 26. I don't know what you want, 10 to minus 10. And then afterwards, you shoot the error, think of that as being very small. Okay, that's standard Channon's formula. Or Channon's formula then is the formula for this capacity expression. Okay. And whatever Shannon's formula is, he computed a formula for this in terms of mutual information. That's not going to be so relevant for us. But what's really important for me is that we're somehow on the same page for the definition of capacity. Okay, and it's like if you're not working daily with it, then okay. But think of I encode this big block, and I'm happy to tolerate some error. Okay. N is equal to 10,000, and the error is 10 to the minus 10. All right, and I'm happy to tolerate that error, and I'm coding for the channel. Yeah, it's okay. Now we make it quantum. Okay, quantum. Nothing changed. Same picture. Okay, you just have to reinterpret it. Okay, decoder is now quantum. The channel is quantum. The encoder is quantum, but just to make things simple, I keep the input bits still classical, keep the output bits still classical. Okay, so it's still this is the formula then for the classical capacity of a quantum channel, ller-Hermes. It also has a formula, the HSW theorem. It's like the formula from before. You have to reinterpret now as phenomenon entropy. You have to regularize, but never mind. The formula is not relevant for us today. That's the setup. Okay, and what you should realize. Okay, so and this is the setup that has been studied. So if you open Nielsen and Shor, like on the last chapters, like this is the setup you study. You open like Mark Wilton's big book on the topic. This is exactly the setup study. And I sort of like saying it's like highly unrealistic, right? I mean, we talked about it before that this is not the setup that we're actually going to have. Because this assumption of noiseless encoder decoder is just unrealistic. You have these errors here. Yeah. So the first question, once you realize this, you may ask, is this possible at all? Is quantum communication possible at all? Maybe this capacity is zero in this case. And it's not so hard to see actually that it's not zero. Okay, it's not completely obvious immediately, but it's not hard to say it's not zero. But for instance, you could say it's the capacity formula from before. Is that still relevant? Or is it kind of like continuous in the gate error? Okay, it's like when I take the whole setup depends on a gate error. Maybe I should. Yeah, the whole setup you see has now two parameters. It has a parameter for the channel, and it has a parameter for the noise strength, delta. And so let me define it, like put it like this here. So capacity at zero noise for this one. Oh, I go over encoder decoder pairs with M input bits, and the capacity at delta noise. So lambda is fixed, so the channel is fixed. Is that same formula, but you go over also encoder decoder pairs, and you can think of maybe using, but really it's just over arbitrary things, right? So but when you evaluate the probability of being correct, you evaluate it after you've thrown this delta noise on the gates according to our noise model. Okay. So it's clearly when you throw noise at it, things don't get better. So clearly the capacity at delta noise is smaller than the capacity at zero noise. Right? It's clear. Question is how much smaller. And it's important for the setup that the noise this gate noise is fixed, right? I mean, that's how I want to think of the threshold theorem, right? I want to have fixed noise. It's not like I make my block bigger and I'm allowed to decrease the noise. So I fix the noise. So it's kind of like a capacity with several parameters or with an additional parameter delta. So we have this, maybe it's not the right way of calling a threshold theorem, but there you can, really it's a capacity bound. So if you now take the construction from before for this, then you actually obtain that the capacity at delta noise is bigger than the capacity at zero noise minus some fudge factor. Okay, so that's what we can show. And the this fudge factor, this factor goes to zero as delta goes to zero. Okay, and then we can go in more detailed discussion. The encoding level can depend on n in the more detailed discussion. We also did this for the entanglement system capacity. And now in this way I explained it, it also works more generally for general noise and for somehow code by code. But I want to state it like this. And I think this is sort of like the theorem that in some sense tells you that, hey, the formulas we know from Shor-Westmoreland and the formulas we have computed in quantum information theory for capacities, yes, they are the right formulas, even though your encoder decoder has a delta noise. And maybe I should, maybe I didn't emphasize this before. You see, the point is that the encoder, right? The encoder here has a quantum output, and the decoder here has a quantum input. Okay, this is why it's not obvious that your normal statement from fault-tolerant quantum computing will work. Right? So normally you would say like, okay, well, I mean, this quantum computer, I know fault-tolerant quantum computing works, but that has a classical output. But here I need to prepare a state to put into the channel, and here I need to measure a state. So then, and I'm a bit out of time. So maybe let me show you very quickly how the proof works. So you basically have two of these machines, right? So what we had seen before is that this machine I can replace. So the left-hand side, this I can replace by some correlated noise, and the perfect encoder. Then comes my channel, and then I can replace this here. I didn't show you, but by a layer of noise and the perfect measurement. And then you have to analyze, well, what is the capacity of this composite thing? So now you think of this being your channel. So it's kind of like your product channel plus a little bit of noise tacked on. You need to analyze what the noise is, what the channel is for this, and you can then show it has a similar capacity to this one. Okay, and but what's the lesson for this is that if you want to decode, your encoder decoder that you're building is not for the original channel. You build it for some kind of an effective channel, and then only you encode. So the fault-tolerant construction in that sense is non-trivial. So you or you consider some robust codes. So right, so you build this thing, but it's not like, oh, the red box here is not just the encoded one for the noiseless case. It's actually the encoder for this one, and the same here. It's a decoder for this one, and so that's maybe a bit of a subtlety, and I think yeah. So we also have some other application, but I think we're just going to jump it. And if you have questions, you can ask me. So we have a new paradigm for fault-tolerant quantum output. I hope I explained to you the relevance of quantum computing. And since it establishes that the standard model for quantum channel theory actually is an appropriate model, it also gives explicit constructions, although there's room for improvement given that we're just using kind of like abstract techniques and don't actually have worked towards making it practical. But I think there's a broader relevance in quantum computing by connecting small quantum computers by commutation lines. And also actually this, like for instance, state preparation is actually a subroutine in many fault-tolerant constructions. And so whenever you have like some subroutines, such it's kind of like, it's an important subroutine in this constant overhead construction that Daniel came up with, and that has now been used in conjunction with these new quantum LDPC codes, and these state preparation procedures you can now slot in also this theorem for that. And so we did that, and it allowed us to kind of like improve the results there to make them also work for general noise. Maybe that's some side contribution. So thanks for your attention.
Questions? Question? Go ahead.
So I understand that the channel capacity for this noise case decreases by a bit by this f of delta. Can I understand it as because when you go to the fault-tolerant regime,
Sorry, say again.
sorry, like the capacity of delta noise is greater than capacity of zero noise minus f delta. Can I understand it as having to do with like that in the fault-tolerant, when we have fault-tolerance quantum computation, there's only like a constant overhead. Is that like the intuitive reason why the capacity drops, but not by a lot?
That just was.
Yeah. So is there an intuitive reason why the capacity drops, but it doesn't drop by a lot? Well, I guess the intuitive reason for this is that the noise is not very strongly correlated. So,
I thought you might have like over rotation on your qubits, so coherent errors are allowed.
that's right. But then you can still like you basically expand the noise operator, right? So if you have over rotation, right, each of them over rotates by a little bit, and then you can expand it in a linear combination of low weight Pauli operators. And then somehow the difficulty is that it's a linear combination and not a probabilistic combination. But one can deal with that. But it is actually true that the statements you will get have different kind of like strength. So if you have a Pauli noise model or a stochastic noise model, you have fewer demands on the codes. Then so then you have so it depends on it depends on what you want to prove. So it is true that when you have these over rotations, then the statements you can make are not as strong as when you go for the stochastic noise model. So there is some difference in the statements. So the early work by ller-Hermes, where I cited theorem now for, they were actually for the stochastic noise model. Maybe only Pauli noise model, but the routines are working now in general. So yeah, it's a more detailed discussion, but we can take later.
Okay, we have 3 hands up. We are a little tight on time. Who is there was one why don't you go ahead and maybe we might have to take the rest offline.
Okay, so maybe very quickly, I'm just curious, does this special type result for channel capacity, is that connected to the standard form of threshold theorem in original error correction? If you take the standard error correction code and you have a threshold result, does that inform anything about what happens in this case? Is there a connection or?
Yeah, no, I mean the constructions are the toolbox of constructions is say similar, right? Or the elements are the same. So it's just that the way I formulated it, so think of the delta being the same.
Okay, so
the threshold being the same.
There is a quantitative connection between.
There is a quantitative connection because the techniques are connected. And depending on which analysis you now do, you would get one or the other. So I don't think that in that sense here we have there's, at least I don't see it a new effect coming in the sense of thresholds would be lower. The statements are more if you're below threshold, right? If you're below threshold, then you get such and such statements, and there you have a certain noise operator on. It's like when you go for the threshold theorem, the way I formulate it, it's just so like the way I formulated it here, you just read this part here, right? You delete this part, right? The rest still makes the same amount of sense, right? Because it's just a statement for f of delta, for delta going to 0. That's why some of the threshold theorem is not so required there.
Okay, so in the interest of staying on the schedule, we're going to go ahead and wrap up. But I did want to mention Professor Christandl is going to be around today and tomorrow, and there are at least a few open slots left on the schedule. So for people who do have additional questions, please feel free to sign up. Thanks, everyone.